If you have an object that's essentially one-dimensional, like a piece of string or a metal rod, right, it doesn't extend very far in most directions, it's mostly in one direction. The linear density of that object is the mass of the object divided by the length of the object. So this gives you some measurement of how much mass is in each unit length of the object. So for an example of something that would have a high linear density is something like a big thick metal chain, right? Every link in the chain weighs quite a lot because it's made of metal, so it's pretty heavy. An example of something that would have a low linear density is something like a thin piece of string, right? So if you had a meter of chain, it's going to weigh a lot more than a meter of string. So that's what linear density is. You may be used to the idea of density. Linear density is mass divided by the length of an object. Regular density is mass divided by the volume of an object. So linear density is sort of a one-dimensional version of density. And the symbol that we're going to use for density is this. It looks like a P, but actually it's rho, R-H-O. It's sort of the Greek version of R, basically. So this is a lowercase rho that we're going to use for density. Just to make sure that we understand sort of how linear density works, let's find the linear density of a rope that's 50 meters long and 3 kilograms in mass. So just using this formula, the linear density, rho, is 50 meters, the length, I'm sorry, this is upside down, 3 kilograms, the mass of the object, divided by the length of the object, which is 50 meters. So this is 3/50ths, and the unit is kilogram per meter, right? So this is saying for every meter of this particular kind of rope, it has 3/50ths of a kilogram of mass. All right. Of course, there's another way we can use this sort of definition. Right here we knew the length and the mass, and we found the linear density. You can turn this around and use it the other way. So suppose that we have a type of wire whose linear density is 1/4 of a kilogram per meter. What is the mass of 18 meters of this wire? So, right, we had the definition that the linear density was the mass divided by the length. We can rearrange this to say that the mass of an object, a one-dimensional object, is the linear density times the length. So we can use this idea. So we get the mass of this object is 1/4 kilograms per meter. So that's the linear density times, now we need the length, and that's 18 meters. Notice that the meter units cancel here, and we just get kilograms for our unit, which is good because we needed a mass, right? We were expecting to get a mass out of this, so it's good that we get mass units. And then, so 1/4 times 18, that's going to be 9/2, or I guess 4.5 kilograms. Okay, now there is one important caveat of this equation that we used here, which is this equation assumes that the linear density must be constant. That is, at every point, if we lay out our linear object here, at every point along this object, the linear density should be the same. So, this inch of wire or rope or whatever it is, this inch of rope weighs the same as this inch of rope, and that weighs the same as this inch of rope, and so on, all along the length of the object. So how could we handle it if the linear density changes as you move along the object? So maybe there's a heavier portion in the middle and the ends are lighter. How could we find the total mass of the object then? So let's have a look at that kind of situation. So let's suppose that the density of a 10 centimeter metal rod varies along its length, right? So we have this rod like this, and its linear density x centimeters from its left end is given by this formula, x plus 2 grams per centimeter. So we're measuring position along this rod by taking the distance from the left-hand end. What is the total mass of this rod? Well, we can't use, we had this formula that mass is equal to linear density times length, but we can't, this is only if the linear density is constant, and this linear density isn't constant, it's a function of x. So we can't use this equation immediately for the entire rod, but what we can do is break the rod up into tiny little pieces, pieces so small that the density doesn't have time to change as we look at just one of these pieces. For a piece to be that small, though, it has to be sort of infinitely small. So at position x, there's a little bit of the rod whose length is dx. So for at the position x, the mass just at that position is the density at that position, which is rho of x, times the length of the bit of rod at that position, which is dx. Now we can find the total mass just by putting together all of these little bits of mass. So integrating rho of x dx. How about our bounds? Well, x is the distance from the left-hand end. So at the left-hand end, x is 0. This rod is 10 centimeters long, so at the right-hand end, it's x is 10 centimeters. We should use centimeters for our units because the linear density is given in grams per centimeters. So the total mass, we just need to integrate from 0 to 10. So we're going to integrate from 0 to 10, x plus 2, because that's our density function. And now this is just a regular integral problem, right? So find an antiderivative, 1/2 x squared plus 2x. Evaluate at 0 and 10. Right, plug in 10, you get, so 100 over 2 is 50, plus 2 times 10 is 20, minus, and then when you plug in the bottom bound 0, you get 0. So this is 70. And this must be grams because we were measuring things in grams. But if we go back up to our formula here, this rho right here, this was in grams per centimeter. dx is a distance, but we were measuring distances in centimeters. And so those distance units cancels, and we do indeed get grams for our units. So, right, this grams, that's not we're not just guessing that we get grams, we actually do get grams from our calculation. All right, so the general idea here is if you have an object, some sort of linear object that extends from one x value to another, say from x to b, and its density is given by some function rho of x, then the total mass of that object is just the integral from a to b of rho of x dx. So this is sort of yet another example of where integrating a function tells you something useful. In this case, it's mass. Let's look at one more example. So let's find the mass of a 2-meter long pipe whose density is the square of the distance from its near end, and that's in meters, and density is in kilograms per meter. So let's see, our density function, it says it's the square of the distance from the near end. So if we call the distance from the near end x, then the square of that is going to be x squared. Okay, so to get the total mass, we just need to integrate this. We're going to integrate x squared dx. And I guess the near end is 0 if we're measuring x from the near end. And the far end, well, it's 2 meters long, so the far end is at x equals 2. So now we can just integrate this. So 1/3 x cubed from 0 to 2. So that's 1/3 times 2 cubed is 8, minus 0 cubed is 0. So 8/3, or 2 2/3, and this is in kilograms because of the units we started with here.